What's up, everybody? My name is Remy, right? Many of you might know me, many might not. I was inspired to do a video just to introduce real quick noise and vibrations and different types of noise and vibrations, and maybe give you like a little bit of an intro into these big words of vibroshocks and all this good stuff. Again, this is going to be really brief. If you have any questions for me, please leave it in the comment below. I always want to do that, YouTuber. Please leave it in the comment below, and we'll get back to you. I'll make another video to address it, or maybe we can just have a LinkedIn chat on it, or whatever it is. All right, so let me describe here. I want to back up before I speak about sound, right? I want to speak about light. Light is very well defined, and it's mainly because we perceive it a lot better, and it's a lot, again, a lot more well defined. Everything is subjective, but with light you have less subjectivity than sound, right? So obviously there are both ways, right? Light is an electromagnetic wave, right? So you have electric field going this way, magnetic field going this way, and they kind of just hold each other out, right? With sound, it's a mechanical wave, right? So you have propagation of pressure, right? So I'm coming, I push you, you push the person in front of you, right? And then I relax. So you got like compression, and then elevation, I think, or I don't know what they call that, but basically you compress, you decompress, and you keep going like this, right? Sound is very cool, right? With everything you have constructive interferences and destructive interferences, and they work a little different in both, right? A lot of people studied this, or you might have studied this in physics, right? Is that you try shining a laser through slits, and you can see it like making a lot of different patterns just from shining in one slit, or like forcing the light through. You're forcing that interferences, or constructive / destructive interferences to make that pattern, right? So let me back up here. I try to keep this short because I tend to talk a lot. For people who know me, you get me talking about physics, I talk. So, all right, sound. So light, right? Light. We have the white light, right? Light from the sun. I'm gonna call it broadband, right? So you got that broadband that packs everything inside of it. It's the full energy, full spectrum light, right? You might be familiar with the Pink Floyd prism, the one on the album, right? On the cover of the album, where you shine that broadband through and it would split it, right? So again, different material properties, different properties of light, but what happened is that you're splitting those into respective colors, right? Red all the way up to blue, violet, and such. Now, why did I mention this? It's because you can think the same thing about sound, right? So you have white noise, right? You might hear that term a lot, white noise. A term that you won't hear a lot is red noise, blue noise, and such. These are basically bands, right? Or some different spectrums that are low energy, high energy, and such. When it goes to sound, right, you're obviously dealing with vibrations, right? Vibrations is you moving something, right? So obviously the first type of vibration you can think of is free vibration. Put a molecule in there and just make it dance, right? That's free vibration. Next type you have is force vibration, right? Which is, think of it as trying to shake somebody, right? So you're force vibrating them. The other type is damped vibration, which is, think of it as shaking somebody against the wall. No, I'm just kidding. It's a lot of anger, but basically it's different types of vibration here. One you're forcing, and the other you're trying to control. Let me put it this way, right? I'm not gonna go very much into damping. I'm gonna only mention a couple of quick things, like when you dampen something, right? There's so many ways to dampen it. Obviously, vibrations depend on the medium is going through, right? Solid, liquid, gas. So whatever that medium is. And then it depends on the property of that medium, right? So you have stiffness or stiffness mesh, right? Inertia, mass, and all other properties if you're talking liquid, viscosity, and flows, and all of the different things, right? Okay, so that's vibrations. Vibration is a little more complicated in liquids, so I'm not going to speak to that, but all I can say is liquids can be used to dampen out vibrations, right? Mass, think of it as mass. And you can give it an inertia, fill a bucket, whatever it is. Yeah, so going from that perspective, right, there is a range, obviously, that we're very interested in sound. So vibration is cool. Think of Inception, right? You're sitting down, you're watching a movie, and out of nowhere, like, something comes up and you start shaking, or when you shoot guns, for example, or when anything happens, vibration. Somebody's angry. Yeah. So vibrations. Very subjective, right? Now we go even more subjective, or subjective in terms of your judgment on it. Acoustics. So acoustics is very relative to us, right? Because acoustics is subjectively, or the psychoacoustic part of things, right? So I'm talking now roughly 20 to 20,000, right? Or 18 to whatever it is, or 36 to whatever it is. It's the hearing range, right? So we're talking hearing range, and when you're talking hearing something, right, you are actively judging it because you are critiquing it, right? Especially if you make music like I do. I love making music, and I like critiquing my music, and a lot of times you hear like rappers or different musicians, they will put in like some small things, or I've always wondered, for example, when I was young, why does the bass instrument exist and such? Like stuff that are very small in the back. But reality is, sound or psychoacoustics is about perception. So to come and define that, right, let's talk sound metrics. You have a lot of metrics in sound, right? Or I would say mainly around 7. Could be more, could be less, depending on how you define things. So I would say sharpness, right? So sharpness is one of the qualities of sound, and sharpness depends on the contribution of high frequencies in the sound, right? So obviously you have a band, right? Whenever you're making sound, you're making a noise, right? Whether it's a significant or something that we can feel and hear, like noticeable noise, or something that we can pick up on, right? Which I'm gonna speak to that later because that's part of the sound metrics. But you're making noise. So sharpness is that contribution from high frequencies into this, right? The opposite is boom, right? So boom is the contribution of low frequencies. I think like up to 225 or something like that into it, right? Or 223 into it, right? So that's the two sides of things here, right? And again, I'm not gonna talk about units because I'll explain why after we're done with this. So you have, like I said, sharpness and boom. Another thing you have is frequency modulations, or fluctuations, or frequency fluctuations, or there's so many terms for it, kind of. But basically, it's when you got like whoom, 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 where you have a modulation frequency where the noise is kind of moving in and out, and I like to dance too, so don't judge me. But basically, you have noise coming in and out, and it's modulating at a certain frequency. Very noticeable, right? Like whoa, whoa, whoa. Now, if you were to take that modulation frequency a lot higher, right, you would get roughness. So I think it's about, I want to say 20 hertz, but you would get roughness, which is like, right? Or think of the Inception movie, right? The start of the Inception movie. I know a cool note, right, is that sports engines or sport car sounds, sport cars sounds, right, is designed from rough or with a contribution from roughness and sharpness, right? Because you want and that high frequency. Can't make it, but So that's that part, right? So you have roughness, frequency modulation. Another one, it's very cool, is tonality, right? Tonality is, think of it as developing that sound, or actually being able to hear and fully develop that sound in your psycho, right? So like think of a lot of people speaking, right? And while they're speaking, I just said a word of what they're saying already in there, so you're not going to really hear it, right? But think of people speaking and then they stopped, and then I said something, and then I stopped, and then they talk, so you're going to be very clearly defining what I'm saying. That's tonality, right? So you can hear that very well. And then of course, overall level. I mean, you want to measure the overall level of whatever you're doing. So that's important. Yeah. So sound metrics or sound quality metrics are very cool because they help you understand more what's happening, right? Or be able to describe, quantify, define what's happening. Because if you define what's happening, you can actually actively, right, go mitigate it or dampen it out or such. So I've described to you the different dampening methods, right? Two things actually in particular I want to describe because I think they're very important is resonance and phasing. And that's in the understanding of vibrations overall. So let's start with resonance. I like to give this example when I talk about, actually there are two examples I like to give. Don't judge me, but just imagine it with me, right? So imagine that you are in a land where it's a desert. I come from Egypt, so you can relate there. It's a desert, right? But there's a piece that's fertile in that land. So you come in there and you're basically putting a stimulus. So you're throwing seeds all over, right? You're going to realize that a lot of those are not growing, but the area in the fertile land is going to grow. Why? Because it's kind of predisposed for that. Let me just, instead of saying predisposed, let me say there's energy stored in it, or the system is set up in a way that it has energy storage in this area. That's what a resonance is. Think of it as a megaphone, right? So you have a megaphone somewhere, you're talking, and once you pass by the resonance, the same exact, sound quality, the same exact everything, just boost because you have the megaphone there, right? Stored, or there's a stored energy there. So that's a resonance. It's very important because resonances can damage the structure. It can actually how do I say this? Compromise the structure of what you're doing, or the structure soundness of what you're doing. So you can break bolts on resonances. Matter of fact, we use in a lot of our daily life, not just for sound, but it's the same for light. We use resonance to optimize whatever we do, but they can also be destructive. Think of a light bulb, right? The very old light bulb, the one with the filament. Basically, it's a light resonance, right? So that's an area where if you were to put that much resistivity in it, it would give that much energy. So that's resonances, right? Another thing I want to speak about, because I think is very, very important, and I think it's like mind-boggling, is phasings, right? So think of me like holding a bucket, right? So I'm just gonna do this, right? So I have those two things, and I started vibrating this, right? Forget about a spring; they're one mess. So when I vibrate the top one, they're just gonna vibrate together, right? So think of me putting a spring in between, right? It's gonna really depend on obviously the material of the spring, the geometry, distance, all the good stuff. But what you can happen is, what you can happen is that you will have some phasing, right? And what that phasing does is that it can actually create destructiveness or constructive interference or destructive interference in your noise, right? How would you know? You're going to have to take a look at the whole system and understand the harmonics and everything. Harmonics is a cool word. I'm going to have to explain it right now. But yes, so phasings is very important because you can have something very strong. And just because you built the system right, you're having like a counterweight, right? Which you might be familiar with this. They do this a lot with motorcycles. Is that the old models that vibrates, they put like a counterweight to it. This way, when they vibrate, the counterweight would actually vibrate the opposite way and dampen out the engine vibrations, because it's hard mounted and it doesn't have rubber in it. Okay, so backing up, harmonics. That's a very cool word. So in order for me to describe that word, let me again briefly talk about meshing, right, or patterns, right? Excuse me. So I'm going to talk about gears, because gears is awesome. They are awesome sometimes. But let me talk about gears, right? So let's say you have a 5-teeth pinion, right? Or a 5-teeth gear, right? Rotating on a 10-tooth or 10-teeth ring gear, right? So they are rotating on top of each other. If you were to take one rotation of the pinion, right, you just hit 5 times, right? 5 times. So that 5 times is your order, right? So that's another new word I'm introducing, order. Order is basically, it's a specific pattern you're looking for. It's a pattern that's happening over and over again. Now, I'm not going to really define the time base, because you can do a lot of things with that. You can assume an order and then track orders on top of the order. But basically all I'm going to say is you're tracking a pattern, right? So let's say 5 times per second, right? So 5 hertz. A harmonic of that, right, is, think of it this way. I'm doing 5. I'm doing another 5. I'm doing another 5. So what's happening is I'm not completely dampening out everything, because I'm actually putting 5, 5, 5. So I'm putting a very strong signal at the 5, but I might actually be getting a 10 as well, right? Which is, it's not really a 5, but think of it as the first 5 didn't fade out, and the second 5 is kind of still coming in. Like it's a harmonic is just propagation of whatever that frequency is, right? Through your noise. Because again, your noise is capturing everything, right? It's a white noise. So if I were to record this, I'm recording everything. But if I'm trying to find out the amplitude of the sound, I'm only going to be looking at my order. So anyway, let me stop it right there. But it's really awesome, right? If you have a specific area that you would like me to talk about, please let me know. I would love to go more about it. Before I go, because I mentioned it and I hate to break my promises, is transfer path. Transfer path, just to say really quick, is the path that noise or vibration takes to travel up something, right? So if I say, I'm just gonna do this, right? So if I'm vibrating my bracelet here, right, and I'm feeling something up here, that my transfer path depends on everything going through here, right? So transfer path analysis is a term usually associated with understanding the whole transfer, right? With the angles and with the weight and stiffness of this, with the combined weight and stiffness of this, is actually understanding the system's transfer path. Or if I were to put one here, if I were to throw one orange here, am I gonna get one orange worth of juice, or what it is, and how does it propagate through? Maybe if I'm going like this, it would actually change my vibrations, which it would. But so it's transfer path analysis. You understand how the noise get from the vibrations get from point A to point B, right? You understand that path, because that path actually contributes to what you get at point B. So if you change the path, right, or the dynamics of the path, you actually get a different point B. Thank you very much. I hope you enjoyed this, and I hope I didn't overwhelm with a lot of information. If you would like anything else in terms of understanding a little more about something, please let me know, and I will make another video. I love to talk about this. If you want me to start speaking about quantum mechanics, I'm not the right person to, but I will. I love it. So just let me know what you want me to speak about. and I'll do it. Thank you very much. I hope that gave you an introduction about NVH or noise overall. Thank you.